So let's just start with that puzzle right there. Imagine you've got this liquid, right? It's so thick and complex that if you try to boil it like you'd boil water, it just scorches. It turns into this solid, completely useless gunk before it ever has a chance to vaporize. So how in the world do you separate out all the good stuff inside?
And the answer? Well, it's brilliant, because it's so simple. You don't try to change the liquid, you change the entire environment around it. You literally change the fundamental rules of what it means to boil.
To really get the solution, we've got to start with the problem itself. And that problem is this thick, nasty stuff that's left over from the very first step of refining crude oil.
It's called atmospheric residue, or Atmos Red for short. Now, this stuff looks like tar, but it is packed with heavy, really valuable molecules. You can turn them into things like lubricating oils or use them as feedstock for other units in the refinery. But here's the catch. Its boiling point is way up there, over 350 degrees Celsius. And at that temperature, with normal air pressure, the molecules just freak out. They break apart and fuse together. It's a process called coking. And just like that, your valuable liquid turns into worthless, solid coke.
So if just heating it up is the big problem, how do you get it to boil at a lower, much safer temperature? Well, you create a massive, industrial-scale void. Think about boiling water for a second. At sea level, it boils at 100 degrees Celsius, right? But if you go to the top of Mount Everest, where the air pressure is way, way lower, it actually boils at only about 71 degrees. The vacuum distillation unit, or VDU, uses that exact same principle. By creating an incredible ultra-low vacuum inside its tower, it just plummets the boiling point of that Atmos residue. Suddenly, the oil can vaporize without getting hot enough to coke. And that lets us separate all its valuable parts and actually, extract their value. And this is the beast that pulls it all off. Now I know, this diagram looks complex, but the idea behind it is actually pretty simple. This whole setup, the overhead system, it's like a super powerful engine built to do one thing and one thing only: create and hold on to that critical vacuum. It's this carefully choreographed dance of steam and water, and we're about to walk through the steps. So here's the play-by-play on how that vacuum is made. First, you've got vapors coming off the top of the tower. Then these powerful steam ejectors kick in. They basically act like giant vacuum cleaners, using jets of steam to suck all that vapor out. Next, aftercoolers chill that mixture down, fast, condensing almost everything back into a liquid. And finally, all that liquid flows into a tank called a hot well, where the oil and water naturally separate. This whole circuit has to work absolutely perfectly, all the time. And this quote, it just drives home how fragile this whole operation really is. That barrier between the vacuum inside and the normal world outside, it's maintained by nothing more than a simple liquid seal and some pipes called dip legs. And as the source material says, if that water level drops just a tiny bit, the seal breaks, air rushes in, and poof, the vacuum is gone. Instantly, the entire unit would have to shut down. Okay, so we've got our Atmos resid boiling away nice and safely under vacuum. But how do we actually separate all the valuable products from that big cloud of vapor? Well, that magic happens inside the tower itself in a process called fractionation. So as these hot vapors rise up through the tower, they start to cool down. And as they cool, they condense back into liquid on these special trays at different levels. The heaviest stuff condenses down near the hot bottom, while the lightest stuff makes it all the way to the cooler top. This lets operators draw off different products at different heights. Way down at the bottom, you get the heaviest stuff, the vacuum residue. Move up a bit and you draw off very heavy vacuum gas oil, or VVHVO. A little higher is the heavy vacuum gas oil, HVGO. And then way up near the top, you get the lightest liquid, the light vacuum gas oil, or LVGO.
But separating these products is only half the battle. I mean, they're being drawn from the tower at incredibly high temperatures. All that heat is valuable energy, and you have to recover it and manage it with absolute precision.
This slide just illustrates the different challenges perfectly. Take a look at the piping on the left for the vac resid. It's pretty straightforward, right? Now, look at the system on the right for the light vacuum gas oil. It is way more complex. And that's because each product, coming from a different temperature zone in the tower, needs its own unique network of pumps and heat exchangers to handle it safely.
So, there are two key terms you hear a lot here: pump-arounds and rundowns. A pump-around is this really clever trick. You take some of the liquid you've drawn off, you cool it down, and then you pump it back into the tower at a higher point. It acts like a precision cooling system to regulate the temperature inside. The rundown, on the other hand, is just what it sounds like. It's the portion of the product that gets fully cooled and then sent on its way, either to a storage tank or another part of the refinery. And getting that balance right is everything for both efficiency and safety.
Which brings us to the most crucial point of this entire process. This thing is a constant, high-stakes balancing act where one tiny mistake can have absolutely massive consequences.
You're facing constant threats. We already saw how catastrophic losing the vacuum is. But inside the tower, if a pump around fails, a section can overheat, causing that coking we talked about, which can literally clog the entire unit from the inside out. And then on the product side, if that heavy vac res isn't kept hot enough, or if it stops flowing, it can solidify into a block of asphalt right inside the pipes, creating a plug you can't imagine.
So the vacuum distillation unit isn't just a tower, it's this incredibly dynamic system that's held in a very delicate, high-energy balance. It's a brilliant solution to what seemed like an impossible problem, boiling the unboilable. And it really leaves you with this one thought. In a process this extreme, where materials are always a few degrees away from either solidifying or burning up, the line between extracting immense value and a catastrophic shutdown, well, it's razor thin. It's all managed by precision, control, and a really deep understanding of physics.